clever, beautiful talk. It was also very, very broad, and this talk is going to be much more narrow. But nonetheless, I hope that it's going to be useful for you guys in part or even in totality. It's going to be focused on dynamic programming. So there's a little web page that I prepared to go along with this talk. And I'm going to be doing this on a Windows machine. By the way, I tried to connect my laptop. I try to promote myself as an expert in computation, and yet the number of times that I have to successfully look up my Linux laptop to the projector is getting embarrassing. But anyway, so I'm going to do that on Windows machine. I haven't used Windows since like 1984 or something. They're also going to help you from the trouble, and we should be all good.
You're making a run assumption that I know Windows.
Okay, we'll work it out together. So we're in this time. So let's start. Okay, so like I said, I made a little web page to accompany this talk. This talk before lunch and the one after lunch. And I believe that Bill sent you the link to it already. If you don't have that, or if you want to locate it later on, you can go to the quanticon.org website. And up the top right, you'll see this little octocat symbol, which is the GitHub symbol. So if you click on that, you'll find the org site, Quanticon, and you'll find a list of repositories. And if you type DSE here, you should find something that says DSE workshop. And that's a page that contains a bit of information about what I'm going to talk about, and a little bit of background and some code that we'll get to. So let me just walk you through what resources we have available, and we'll take it from there. All right, so in terms of the topic I'm going to speak about is dynamic programming. So I fear I'm the only person here that doesn't do structural estimation. And I hugely admire the field of structural estimation, and I find it fascinating, and also a great source of applications for one of my favorite fields, which is dynamic programming. So I've been working on dynamic programming topics for quite a while, and now I've been writing a textbook with John Stachurski, and that textbook is just coming towards completion. And the textbook has a bunch of slides that go along with it. And what I'm going to do is I'm going to pick out some of those slides and cover the material in there. And I'm going to do it in a fairly breezy, fast-moving sort of a way. So I feel like it's going to be hard maybe to follow every single detail. But the idea is that the slides are there. And then if there's not enough detail in the slides for you, there's the textbook behind it. And that has all of the proofs in painstaking detail. So hopefully, even if I do go a little bit quickly in places, you'll be able to work back through whatever's interesting. I think it'll be better if I give this kind of like overview, broader picture, and then you can dive into specific parts. And then as you do that, if you do it later on, feel free to ask me questions or send me emails or whatever you want to do. And also for this talk, as I go along, I'm very happy to make this chatty and interactive. So if I am going a little bit quickly, if I skip through some terminology, there will be a bit of notation, a bit of terminology. If I skip something over, or even if you just plain forget, feel free to just put up your hand and ask me, what's that sigma thingy over there, and I'll repeat the definition. All right, so the textbook. Let's have a look at the GitHub repository for the textbook. So the book itself is nearly complete. In fact, it's pretty much done. So it's this one here. It's called DP, the PDF. So if you click on that one, you'll find the image of the start of the textbook. And rather than trying to read it in the browser on GitHub, what you can do is you can click on this download button here. So please feel free to, like, it is 8 megabytes. If you're happy with that download, then please go ahead and grab a copy for yourselves. And we're going to be working through the slides of some portion of this textbook. Now, the textbook is not quite finished, it's essentially written, but the very last chapter requires proofreading. All the other chapters have been proofread to some degree. There will be typos in there. The word parts are written fairly quickly. So I don't encourage you to share this textbook too widely at this point. You know, probably publicly release it like in a week or so. I've been in a reading group. I've been working with Shu and Jimmy over there. We've been going through some of the chapters. We haven't got to chapter 7 yet. So there'll be more typos in chapter 7 than everyone else. But hopefully it's already at the point where it's a useful resource. If you do find errors, feel free to contact me by email, or you can open up an issue tracker if you like. Let's click on that and start a new issue and tell me about any issues that you find, any typos, anything you like, anything you dislike, any complaints. We'll take those as well. Now, there's a set of slides that accompanies the book, and I've got slides up to chapter 6 so far, and we're going to touch on the slides from chapter 1 and chapter 6. Can I hide this guy again? Hide this guy? No, sorry. This one. Okay, so we're going to be talking through some of the slides behind the textbook. The agenda, what we're going to talk about, what was advertised, what Phil asked me to talk about, was points 4 and 5 there. So refactoring dynamic programming sounds a little bit strange, but it's a simple idea of manipulating dynamic program to try to deal with something that John talked about a little bit, which is the curse of dimensionality. And that's an interesting topic in the practice of dynamic programming. And we'll be looking at some of the theory behind that and just how far we can push those ideas to make dynamic programming more efficient. We'll also look at implementing dynamic programming and implementing some algorithms. And I'll show you some fun things using Python and GPUs, hopefully, if I can get this computer to collaborate with what I want to do. But before we get there, I need to give you some background. And the way that I'll give you background is we'll start with number 1, which is an introduction to dynamic programming by John Stachurski. And the idea here is that, so has everyone here seen a Bellman equation? Familiar with Bellman equations? Okay, it's fine. I'm thinking 99% of people. So that's good. Yeah, so what we'll do is we'll look at job search. Job search is like a super simple Bellman equation. And I want to walk through that because A, we get a chance to reduce the dimensionality in the particular version of the problem that I'm going to look at. And that's a topic that I want to speak to later, so I'd like to look at it in a practical setting. And B, because I'm going to introduce a bit of terminology about things like greedy policies and various kinds of algorithms and so on. And I want you to be familiar with that terminology. And it's easiest to do that in a simple setting. We'll do job search, nice and simple. And then once we've done that, we'll shift to a broader look at dynamic programming and the underlying theory. And then some of the algorithms we can bring to bear to solve dynamic programs. And then we'll connect these to the last couple of topics, refactoring and then implementing. So that's the rough plan. Alrighty, so then let's go to the first set of slides. The first set of slides is going to be, just funding on this step there. The first set of slides are the slides for chapter 1. Like I said, if you go to the repo for the textbook, you'll see slides. And if you click on slides, you'll find chapter 1 slides. So click through those and you'll do over there. We find something that looks like this. So if you'd like to follow along with the slides, that's the way to do it. But I'll talk through it up here as well. All right, so this lecture, we're not going to go through the whole of this lecture. Like I said, these slides are slides for the whole textbook. I'm just going to pick out little bits and pieces that I want to chat to you guys about today. And so I'm going to skip through the start of it, skip over the symbols and things like that, and we'll just kind of work this out together as we go along. Sometimes you'll see I do things like take absolute values of vectors. But whenever you're not sure about what I'm doing on a vector, like it looks like it should be a number and I'm doing it to a vector, I always mean quantifies. It's the same way you think about doing things in MATLAB or Python or Julia. We can skip over that. There's a 2-minute introduction to Julia. The reason that I've got Julia there is that when we write code in the textbook, we use Julia. Any Julia programs? We chose Julia not because it's enormously popular, but rather because it's open source, so anyone can use it. And it's quite a nice, efficient programming language. And primarily because Julia is quite close to the mathematics. So if you want to describe mathematics with a programming language, Julia is pretty good at getting you close to the maths. So for example, if I want to define a function where f maps x into 2x, I can write it just like that. There's other examples as well. This is a nice language for expressing that's quite good. Going with Julia, but when I show you code, I'm going to show you Python. Not because Python is not quite as pretty as the Julia, but it's good for brute forcing problems and dealing with GPUs and all kinds of things. So that's why we'll be using Python later on. Okay, so I'm going to leap ahead to page, let's say, 35, I think it is. Yeah. But like I said, we'll start with job search. So in this job search problem, simple as we can possibly take it to be, we've got a worker. The worker lives forever. She's going to start off unemployed in the first period. And each period, she observes a wage offer. And the wage offers, I'm going to denote them by W. WT is the wage offer times T. And these are going to be identity draws from a fixed distribution, which is called phi or p, depending on how you like to pronounce it. And my Greek friends always say p, so I try and copy them. It's the p. Yeah, so that's just a distribution. It's actually going to be a finite distribution. We keep everything finite because it saves us from dealing with unpleasant things that I don't want to talk about today. So this is like a probability math function. Beta is going to be a discount factor, and C is going to be unemployment compensation. So the situation for this worker is that she wakes up, she's unemployed, she wakes up in the morning, she observes her current wage offer, WT. She either accepts it, in which case she's going to work forever at this wage, or she rejects it, she gets unemployment compensation C, and she goes to the next period, and she can decide again. Not wildly realistic, but aiming simplicity at this one. So the problem is we need to decide whether to accept or to reject. What do we get if we accept? Well, remembering that jobs are permanent, if I accept at wage W, little w, then I'm going to get W today and beta W tomorrow. I'm discounting, just discounting get present values. And I take the infinite sum, and that's my stopping value. This is the value I get if I accept. That's pretty straightforward. What do I get if I decide to reject? If I reject, I get unemployment compensation. I go to the next period, and I get the chance to behave optimally again. And if I do so, I get the most value I can get from tomorrow. And then if I know that value, then I can kind of do backwards induction to the day, and I can say, well, which one do I want to do? But figuring out which one I want to do, my optimal choice depends on the value of optimal choices. So it's like a tail chasing problem. And of course, when we get a tail shaping problem, the relevant mathematics for solving that is fixed-point theory. In this case, Bellman equations and contraction methods. So let's just go over the details of that really quickly. So, as all of you know, maybe not from this particular problem, but from very similar ones, what we do is we introduce a value function. I'm going to call the value function V star. And V star of W is going to be the maximal value I can get starting from today, given that I've got wage, I've got little W in hand. That's the definition. I'll define it a bit more precisely later. That's the definition we work with now. So if we know the value function, then I can work out the continuation value. If I wait until tomorrow to get, let's say I get W prime tomorrow, and then I get V star of W prime is going to be my value that I get from tomorrow, given that I'm acting optimally. And I'm going to take an expectation because I don't know what value, I don't know what W prime I'm going to get, but I do know the distribution. So I take an expectation, I discount it. I also get unemployment compensation if I decide to wait. So that's my continuation value. That's the value I get if I decide to continue. So if I know V star, then I know my continuation value. And once I know my continuation value, I know my optimal choices. I'm going to stop if the stopping value, which is W of 1 minus beta, exceeds the continuation value, and otherwise I'm going to keep going. And just as a matter of notation, the way that I've written it here, this one is an indicator function. So it's going to be 1 if this statement is true, and it's going to be 0 if it's false. And the idea is that 1 indicates something. So 1 if I act, 0 if I don't act. I just go to the next period. That's just the convention. Okay, so what we've said so far is that if we know V star, then we know how to act in an optimal way. So all that remains now is to calculate V star. How can we do that? Well, we use the brilliant ideas of Richard Bellman. In particular, we use the fact that the Bellman equation is going to hold for V star. Put it differently, V star is going to satisfy the Bellman equation. So Tom Sutton says Bellman's equation. Apparently Robert Lucas insists that we should all take Bellman's equation, and then he says Bellman's equation, and he even says Bellman's equation, and we just arrived at this convention, and I'm going to say it like backwards and forwards the whole time, but you'll know what I mean. This is an equation that we've seen in various forms many, many times, and we get to the point where we start to dream in terms of Bellman equations, and then we know that we're a good economist. That's the definition. And yeah, so this Bellman equation here is a fairly straightforward one because we've only got 2 choices. So if I decide to stop, I'm going to get this value. If I decide to continue, this is my maximal value. And if I choose optimally between them, I get the maximum value I can extract starting today, given that I've got little W in hand. So V star should satisfy this equation. It's not the definition of V star, but V star should satisfy it. It makes sense. We'll talk about proofs later. But just intuitively, this seems to work. Okay, so now we've got this recursive expression that V star should satisfy. And we're going to use this expression to solve out for V star. So this is a restriction, V star should satisfy it. Let's use this equation to figure out what V star is. And we're going to do it in the obvious way, using Bellman operators. Now for that, we need a little bit of fixed point theory, but I'm sure that you guys know the basics of fixed point theory already, so we can skip all this stuff. Contraction mappings and user methods we'll talk a little bit about later. And go on to this point here. So I've jumped to page 74. Okay, so we introduced the Bellman operator. And the Bellman operator is designed with one thing in mind. It's designed with the idea that fixed points of this operator coincide with solutions to Bellman's equation. So if it's a V, that's a fixed point, TV equals V, right? And you can imagine I can do T here, and I get a V that satisfies Bellman's equation. So now all I have to worry about is fixed points of the Bellman operator. And if you've done any dynamic programming at all, and it sounds like almost everyone here has, you're going to know that in most instances, for regular problems, T is going to be a contraction mapping with respect to this norm here, it's called the supremum norm. These are the vectors. Everything's a vector here. Remember that the little w's are finite in this case. So when I think of solving out for B, I've kind of written it like a function, but it's just an array of numbers, finite array, finite vector of numbers. I'll solve that guy. So I think about vectors, and this supremum norm just takes the absolute value of every element in the vector and then takes the mass. And T is a contraction on the set of vectors. So again, I've written, in case you're not familiar with this symbol here, so this W, cap W is the set of all possible wage values. And R is just a real, so this is the set of all functions from cap W into the reals. In other words, it's just all of these kind of functions, candidate value functions. But cap W is finite, so these are just vectors. They're just vectors, nothing else. Okay, and then we can go through the steps of the proof, but I think we're going to skip over it in the interest of time. There's really elementary bound here that I use all the time that holds for real numbers. And from that, it's trivial to show that T is going to be a contraction mapping, which means that this statement holds here. And as soon as we know that, this is beta discount factor. As soon as we see this, just remember that I'm supposed to point with the mouth for the Zoom audience. As soon as we see this expression here and beta is less than 1, we know it's a contraction mapping. T has a unique fixed point. And if we iterate with T, pick a starting point, we apply T and apply it again, we generate the sequence of vectors which is converging to the fixed point. Okay, so that's what this slide says. Also, we had a theorem which we haven't proved, but we'll get to proofs a little bit later. We'll probably skip over that as well. But, so it's fairly straightforward to prove that V star satisfies the Bellman equation. Come back to that. The V star is the value function. And that means it's a fixed point of the Bellman operator. Right? It's just the same thing. And the Bellman operator only has one fixed point. So it's the unique fixed point of the Bellman operator. And everything converges. So now we know how to calculate V star. So we had this problem like, how do we solve optimal choices? Well, we need V star. Now we know how to get V star. We just take this Bellman operator, apply it, we iterate it. So we go through that process. We pick an initial V. We start iterating this guy. So this just means I've applied it k times starting point B. And you know, as long as k is sufficiently large, it's going to be close to the value function. And imagining for a moment that we actually computed the value function, of course, we're going to be approximating here. But imagine that we actually knew this guy, and I've got V star, and then I've got the continuation value, and then I've got my optimal decision rule. Any questions on what I just covered? All right, so let's just change the language a little bit. I want to move to thinking about policies so we can be a bit more precise when we start thinking about optimality. So far, I've talked about optimality and optimal policies and optimal decision tools in a slightly imprecise way. We want to be a bit more precise as we go along, not just for the sake of precision, but also because we care about algorithms. And when we think about algorithms, we have to be pretty precise. So let's slowly try and bring this towards more precise language. And let's talk for a moment about policies. So these policies, like the decision rules that John talked about, they're generally going to depend on, they're going to be actions or decisions. I'll call them actions. I'll denote them by cap A. So cap AT is the decision that the controller or the agent, in this case the unemployed person, makes a decision, makes a time.
John, there's a question from the online audience. What are the sufficient conditions for a unique element?
The sufficient conditions for a unique value function. So the value function is actually always uniquely defined. It's just defined as the maximum lifetime value that we can get. So that's one thing. And then a separate issue is fixed points of the development operator. Now, in this case, we know that they coincide, but that's not always going to be true. And then I suppose maybe what the question is about is sufficient conditions for the development operator to have a unique fixed point. That's a really good question. And in the problems that we're going to consider, that's always going to be the case. And it's always going to be the case because there are always going to be contractions. And there are always going to be contractions because we're going to restrict attention to relatively simple preference structures and relatively simple ways of thinking about discounting. Now, as we start to get into more sophisticated preferences, that kind of thing can break down. And then we need to look at other sufficient conditions. And that's probably not something I have time to touch on today, but there is a discussion already in chapter 4 of the textbook and also chapter 7. So hopefully that answers the online question, and if not, please feel free to get in touch with me and I'll try to provide more details. Has anyone here speaking of preferences and things? Does anyone use something like X times in preferences here? Risk sensitive preferences? Other kinds of non-linear recursive preferences? So these things are getting more and more popular, and they do take us outside the world of contractions and into slightly more complex territory. And I'm not going to have time to talk about that today, but it is explored in the textbook if people are interested in having a chat about it.
I can supplement say maybe more examples. German speaker will not have a contraction. We're going to talk about games with multiplicity. So we'll come back to this. Thanks for your question.
Great. Okay, so let's go back to talk about actions and policies. So when we choose actions, we're going to forbid time travel. So people can't see what happens in the future. So basically, people in our model, they're going to know distributions. They're going to have an idea of like the probability distributions of things happening, but they don't get to see actual realizations of random variables in the future. So in particular, when we think of action, the action times T, can only depend on past history or history up until time T. So we could think in a really general sense of the action being a function, and I'll give it as sigma T, of the elements of the process that we've observed up until time T, which is basically lag states in action. This function is called a policy function. That's a very general sort of a policy function, but these, at this level of generality, dynamic programming is hard to do. Dynamic programming is hard enough already. So let's try and reduce the level of difficulty a little bit. And we're going to we're going to assume that the model has been constructed so that when we make decisions, it's enough to know the current state. Okay, so it's enough to know the current state. So what does that mean? That means that, you know, if I'm trying to work out, let's do a retailer, for example, I had an example earlier in the slides, which I didn't cover, but, you know, someone who's trying to manage inventory, and then think about, in order to decide their inventory for their items, what they need to know to make that decision. And we're going to pack that all into the current state. Now, it's easy to imagine that we could go too far. Right? If I think about everything that a bookseller needs to know to manage inventories of all of their books, like what their competitors are doing, their prices, all these different things, the state is going to become extremely large. We're going to be measuring a huge amount of quantities, and it's going to be unmanageable. So we're looking for that sweet spot where we put enough information in the current state to make decisions, but not so large that the state and the dynamic program itself becomes unmanageable. And we had one favorite Tom Sargent saying in John Ross's book about economic models being probability distributions on a sequence space. This is another favorite Tom Sargent saying, is finding the state as an art. So dynamic programming, we like to think of it as science, but finding the state can be tricky. It's a process of iteration. All right, but if we do things successfully, then our actions can be written as a function of the current state. And we're going to assume that's the case for the rest of the world. And you'll notice that I've dropped a little time subscript here. I had a little T there to indicate that the policy that we're choosing might depend on time. But if you want to, you can always include time in the state variables. Without loss of generality, I'm going to drop the subscript and say that the action is going to be some stationary function of the current state. And that's going to be crucial for all of the theory. Okay, so what we've really done so far is add a little bit more language to this. And the reason I'm doing that, like I said, is because I want to bring this closer to general theory, so we can talk about algorithms. And to do that, I need to talk a little bit more about notation and terminology. So we've now agreed that a policy is a map from states into actions. And for our job seeker, that means that we're going to have a map that takes the current wage offer and gives us a binary decision. It's just a 0-1 in distance. It's a very small action space. With why I chose this problem to illustrate this. It's a simple problem. The policy is just a map from wage offers into 0-1. You've got to accept, not going to reject. Cap sigma is going to be the set of all programs. And then given a candidate value function, some V here, I'm going to say that a policy is B greedy if this statement is true. Again, I'm using that indicator function, so it can be 0 or 1, depending on what I see here. So the idea with a B greedy policy, and this basic idea is going to carry on throughout what we do, is that you treat B like it's the value function. The terminology is not that common in economics, but in like reinforcement learning and artificial intelligence, they use this kind of terminology to understand. Okay, so the idea is think of B as the value function, and it's like the value function or an approximation of the value function. I use it to compute my continuation value, I compare it to the stopping value, and I decide what to do. So that's all of B reinforcements. Treat B like the value function and act accordingly. So with this new terminology, we can say what we've already said in a slightly different way. We can say that the agent should adopt the B star greedy policy. This is sometimes called Bellman's principle of optimality. It's like these fundamental ideas. And through that, we reduce this infinite horizon problem down to a two-period problem, essentially. Which is what we're doing when we pick the green policy, comparing today and tomorrow. All right, there's a little bit of discussion here about reservation wages. We can kind of skip over that. And go on to computation. All right, so with computation, we basically already expressed one way of solving for the optimal policy, at least approximately. And that was we're going to pick an initial V and take the Bellman operator, we're going to iterate a bunch of times until I get close to V star. Now I've got something close to V star, I'm going to take that guy and compute a green policy. And that's going to give me an approximately optimal policy. If I actually get to V star, it's going to be exact one. So that process is one that you're probably well familiar with. That's called value function iteration. And that's probably the most popular standard approach to solving dynamic programs. I want to talk about a couple of other algorithms as well. This is the most standard one. So that's value function iteration.
Is there a way to probably make a guess about the Is there a way to verify that guess was wrong or correct?
So the theory, the fact that it's a diffraction mapping is going to tell us that in a sense, I guess doesn't matter. This is globally convergent.
No matter what we choose.
No matter what we choose. That's one way to answer the question. But maybe, and this is close to what you're thinking, is that actually what we choose is going to matter in terms of efficiency. If I choose something way over here, it's going to take a long time. If I'm a little bit smart and I think, well, what's the value function look like here? Maybe it's going to look something like this. And then take a smart guess. Maybe the computer faster. But with value function iteration, one of the reasons that it's popular is we have this complete robustness. At least in this context. All right, so there's a little bit of Julia code for solving this. And I'm going to
What's the question here from my audience? What happens if phi is above limits?
yeah, so that's a good question, and it's one that I'm going to avoid. But if phi is not known exactly, that takes us more into the realm of potentially structural econometrics. We're going to put some parameters in there, and we're going to solve the problem, and we're going to look at the outputs, we're going to compare the outputs in the real world. And then potentially going to shift these guys around to try and match up with what we see in the real world. There would be other ways of thinking about that problem. And so John talked a little bit about something called Q-learning, which is when we don't know the transition laws. And we use these stochastic approximation procedures. And I'll come back to that and talk a little bit more about that. But let me defer that discussion. But thanks for the question. Okay, so where was I? So we did a little bit of Julia. We saw the Julia code, but let's not do Julia and Python together in one day. Otherwise, we'll confuse ourselves. This shows the process of value function iteration. I took a really random initial guess, and then I applied the Bellman operator, and I got a function that was something like that, and I applied it again, and I got this green line. I applied it 1,000 times, and I got the black line. And by that time, we're essentially stationary. We've successfully computed the value function for this function. Now, having said that, what we've done is we've just solved this problem in the most kind of like plain vanilla dynamic programming procedure that we can. Value function iteration without thinking too much about the structure of the problem. But in many cases, when we look at dynamic programs, we can rearrange things in ways that lead to greater efficiency. And I feel like I'm teaching my grandmother some eggs here because structural time nutritionists are masters of doing exactly this, finding clever ways to rearrange dynamic programs, make them more efficient. So what I'm going to do, and what I hope will contribute a little bit to this discussion, is I'm going to think about that whole idea a little bit more systematically, and think how we can connect this not just to value function duration, but to some other algorithms that we might find more efficient in this. But before we get there, let's just look at this particular problem and see how we can rearrange this problem. You might know this trick already. It's pretty standard for this model. Or variations on this trick. The way I'm going to reduce dimensionality for this particular problem. So what I'm going to do is I'm going to look at the Bellman equation. So the Bellman equation is the first equation, the top of the slide. And I'm going to stare at that, and I'm going to take the far right hand side. I have a continuation value there. You might remember that this whole second choice, I refer to that as the continuation value, maximal value I get from continuing, and I call it H star. So all I'm going to do is I'm going to take H star, I'm going to put it in there. And that's what I've done here. And just because I felt like it, I'm going to put a little prime on the W, but I haven't changed it. And now what I'm going to do is I'm going to take this guy and I'm going to try and transform it into H star. So how would I transform that into H star? Well, what I can do is I can multiply by 5, and then I can sum it, and then I could multiply by beta, and then I could add C, and by the time I did all of these things here, I would change it into H star. But of course, when I did that, I have to do the same thing to the other side. So while I'm busy changing this guy into H star, I'm going to do the same things to this guy, and I get the equality at the bottom of the slide. So now I've got an equality in H star, where H star is the unknown. So we've gone from B star being the unknown to H star being the unknown. Now the point of that, the value of this is that B star is a vector. And it's a vector in, I don't know, it's really like R100 if there's 100 possible H stars. But H star is just a number, it's just a scale. The solving for H star is much easier than solving for B star. In particular, if I want to solve for H star here, what I can do, well, this is a nonlinear equation, right? How do I solve nonlinear equation? There's a variety of different approaches we can use to solve this nonlinear equation for H star. But one way would be to proceed very much like we do when we try and solve the Bellman equation. That is, we introduce a function, which I call g, such that if I find an h with g of h equals h, I have a solution to the equation. So I design g such that an h satisfying g of h equals h is going to be a solution to equation 3. And now I'm going to say, hey, well, g is a pretty nice function. In fact, it's a contraction now. It looks something like that. So we just take this function, and because it's also a contraction, I can start anywhere. Just apply g and apply again, and apply again, apply again, and I'm going to converge to H star. So you've all seen 45-degree diagrams before. There's a 45-degree line. I'm going to pick an initial guess and apply the function. I'm going to go to here, to here, to here, to here, to here. And as I iterate, doesn't matter where I start off. I start off here or down there, wherever. I'm going to converge to H star. Once I've got H star, I've got the continuation value. Once I've got the continuation value, I can compute the optimal pulse. Okay,
super simple problem. All I wanted to illustrate, apart from a bit of terminology, is that if we play around with the dynamic program a little bit, then we can potentially reduce dimensionality and maybe even a lot. And often it's the case that after we project the problem into a lower dimensional space, we can solve it here much more efficiently, and we get the same solution that we get in terms of multiple policies by solving this higher dimensional space. So one of the things we want to do is think about that idea a little bit more systematically and try and understand it, how it works, push it, test the limits of it, apply it not just the value configuration, but other ways.
That's this trick depends on the choice, the kind of choice.
Doesn't it depend on the discrete choice? I think not. You would have to replace the sum with an integral. But I think that would be the only difference. So I think it would work even in continuous state space as well. One thing that it does depend on is the IID assumption. If I go beyond that and assume that waves are Markov, then my continuation value, if I think about future values, that's going to depend on the current state. Because no wave is going to affect future waves. I've got correlation. So suddenly now each star is a function of W, and I've just gone from one function of W to another function of W. I haven't helped myself at all. So I think, yeah, switching to continuous, we could still use this trick, but maybe going beyond that, we're running into problems. And maybe that just teaches us that the way that we can solve these problems is very problem specific. We have to stare at our problems and see if there's some kind of tricks we can apply. But we'll try and unify these ideas as we go along. Okay, so at this point, I'm going to jump out of these slides. And I'm going to go to another set of slides.
John, there's another question here.
Yeah.
About whether you can always get a single fixed point like this. I guess the question is, does the element, the contraction that of the original problem always kind of carry over to modify?
That's a really good question. And I'm going to answer that in affirmative, but I'll do it a little bit later in the talk. But essentially the answer is yes. Okay, so let's do it like this. So now we're going to go to slides. Okay, so what I'm doing is I'm back at the repository for the book itself. This is the dynamic programming book. And I'm going back to slides. And in slides, chapter 6. I'm going to go to chapter 6. I'm going to click on that guide. And I'm going to download it. And then I'm going to ask Pedro to find this file and get that. That doesn't involve. No. So I downloaded this guide. All right, help me out. Yeah, let me just bring it up and after that.
Is this the right way?
Yeah.
Well, worse.
Yeah. I think we did it. Okay, so how are we going to find it? We've got lunch at 12, is it?
No. Is it
12:30?
12:15.
12:15.
Yeah.
Okay.
35 minutes.
Okay, good. So let's push on it. How are you guys doing? Any questions, comments? Yeah.
Sure, I have a question. So in this particular problem, it's enough to know in this case whether it can become false because it's just simple for all pages or some special one. But it's not always possible to recover value or false function from the investigation. Right?
Yeah, so that's right. So, yeah, I mean, I guess that all I can say is that this whole curriculum is a very specific problem. And yeah, so I think that's a good point as well. And yeah, to a degree, the way that these tricks are done are different across problems, but there's an element of similarity. So let me come back to that, and I'll try and unify it a bit, and then we can pick it apart a little bit more and see what are the limits and where it breaks down.
I have a question about reference equation. So in your example, you use the matrix model. So I know in finite dimension, moment equivalent, but in terms of computational speed or efficiency, are they different? Are they a huge difference between them?
Do you mean computing the norm itself, or do you mean the speed of the algorithm?
Still, using it.
The speed of the algorithm, yeah, so the rate of convergence, that's a good question. So you would get a contraction mapping, you would not get a contraction mapping with respect to all norms. But at the end of the day, you know, we talk about vectors converging to a vector, and the rate of convergence is given in some sense. I mean, it's just converging, right? And then it converges. Now, how you measure that? I think once we start talking about speed and rates of convergence, you'll find that the rate of convergence is always going to be essentially the same. It's what's called a linear rate of convergence. And I'll come back to that as well a little bit later on. Yeah. So some algorithms have faster rates of convergence to value function iteration. And that's something that we're going to be concerned with because we're interested in as much efficiency as possible, especially when we do something like structural estimation, where we need to solve the dynamic program many times. All of the things that I've talked about, thinking about solving these problems efficiently by applying different techniques, and sometimes the combination of these different techniques. It's kind of where we go. Okay, so I'm going to jump now to chapter 6, which is a bit of a big jump, but chapter 6 is fairly self-contained. And the topic of this chapter is Markov decision processes. So Markov decision processes is a class of dynamic programming problems, which is so broad as to include almost all of the dynamic programs that we deal with day to day in fields like macro, structural estimation, etc. So in this lecture, what I'm going to do is I'm going to lay out the bits and pieces that build a Markov decision process, the primitives of it. And then we'll talk about optimality. And we're going to be a little bit more careful now. We're going to define exactly what optimality is. We're going to be a little bit more precise in our statements about things like value functions. And once we've got these more precise ideas in our minds, we're going to shift to algorithms and figure out how to solve optimal policy, which is what we will get to. So Markov decision processes, as I said, they're a class of dynamic programs. They're broad enough to encompass just about all of what is going to be discussed in this workshop in terms of individual problems. Once we get to games and things like that with multiple agents, but if we look at the decision problems of individual agents, they're all going to be Markov decision processes, unless we want to get into more fancy things like Einstein's preferences and nonlinearities. Let's put that aside for now. So, to cut the story short, the Markov decision process is the dynamic programming problem where lifetime reward is an expected discounted sum of period rewards. So these BRTs here, these are the period rewards. In the case of dot search, with just earnings, but they might also be something like profit profits for a firm, or they might be utility or consumption for a consumer. However, when we think about dynamic programming, we have to remember that we're not trying to maximize period rewards. We're trying to maximize lifetime rewards. That's our objective function. That's the thing we care about. And so we need some way of aggregating this flow of period rewards into lifetime rewards. And this is the most standard and most traditional way to do it. And if you're doing that, we're working in the world of one-off decision process. If you want to go beyond that, into more sophisticated model of preferences and aggregation, that discussion is in chapter 7 of the textbook, and I'm going to put that aside for a bit.
Yes, the period report constant depend on.
I will get to that in like 2 slides, I think. Yeah, let me be more specific on exactly what that's going to be. But it's random. Okay, so this is the setup we're going to work in. We have a status, we'll call it capex, and it's going to be finite. And we have an action space, an action set, that's capital, that's going to be finite as well. So I'm keeping everything finite here so that we can focus on the computational aspects without worrying about deeper mathematical things like measurability and so on that we really don't want to worry about today. Focusing on computation, keeping things finite. And in this setting, a correspondence gamma from states to actions is going to be a map that takes an X, a state, and gives us a subset of the set of all actions. And the interpretation of this subset of the action spaces is going to be the set of feasible actions at this particular state. So if you think of the job search problem, when you are unemployed, you could either become employed or you could stay in 0 1. But once you became employed, it was permanent. So you had no more choices. Your action depends on the state. Or the set of available actions depends on the state. That's capturing this. Or it might be a budget constraint or something. All right, and then to answer Shu's question, the flow rewards, the 1 period rewards, are going to be a function of the state and the action. So we've got a controller or an agent to observe the current state and respond to an action. From that, they get a reward, given some reward function. And then this is how we aggregate it. This is how we put it all together. Expected discounted sum, net present value. Okay, and then the way that we think about actions is going to be exactly like we said before. You know, allowed to unravel and see the future, not clairvoyance. Therefore, actions have to depend on past states. And in fact, we're going to be very clever in designing the state so that all we need to know is the current state. So actions are going to be some function of the current state. That function will always be denoted by sigma, and we'll call it a policy function. And then I guess this is really repeating what I said before, is that action can be restricted by some feasible correspondence. So gamma of X is going to tell us the set of actions that are available at X. And the graph of this correspondence, which is this set here, that's just all of the state action pairs. So this, whatever you see is G here, it's just the set of states and actions that go with this. That's what G means.
No, that's a question here from the online audience. What are the assumption requirements for them to fall into the market decision process? And specifically, he has or she has like context when developers assume that it's a market decision.
Yeah, okay, so I suppose the way that people define markup decision processes might vary a little bit in the literature, but hopefully the one that I'm using is pretty standard. So I'm in like 2 slides, I'm going to formally define the markup decision process. So I'll give a formal answer to that question. But the casual answer to that question is I really just need to be aggregating lifetime rewards in the way that we see here. Now, again, if you are interested in something like risk-sensitive preferences or Epstein-Barr preferences, so if we're modeling a consumer, let's say, and we start to think about, you know, we're trying to match the data and we're struggling to do so. If you work in asset pricing, for example, you will know that there's a lot of these puzzles, like the risk premium puzzle. And what they're basically saying is that if we take a model like this and we try and fit it to the data, we're going to struggle. And so we need to think like, well, maybe consumers don't like aggregate lifetime utility this way. Maybe they aggregate it in some more general way. And so we write down clever models about how they aggregate things. And that's going to give us different expressions, and that's going to take us outside the world of markup decision processes. So it's really a question of like how we want to model things. And hopefully you're going to find a problem where you can stay within this world and everything's going to be super well behaved. But again, if you have something like asset pricing, you'll find that most of the quantitative literature has moved beyond this because they simply can't match the data with these kind of things. Okay, so hopefully that answers the question in an intuitive way. I'm going to answer it a little bit formally. I just need to introduce one more piece of terminology. So stochastic kernel, all I mean by this sounds fancy. All it is I'm saying, this is how the state's going to update. This is how the state's going to update. So the way it works is, I've got a state, I choose an action, and now I've got a distribution of the tomorrow state. So all it's saying is, if you the state of the world, I choose an action, that's going to affect how the state evolves. So just like the job seeker, you know, when they choose to become employed, that changes the state. You know, the employed will affect. Right? If I'm a consumer and I choose to save a given amount, that's going to affect the state of the world like how much wealth. But it can be stochastic. So this is allowing it to be.
We could have every day from time 0 to time t into the app store, everything can be more powerful to just extend it.
Yeah, so that's exactly right. Formally, everything can be marked off because we just about everything. If we make the state space large enough. But the formal answer is everything's not basically an approximation. But if we do that, we could potentially have an enormous state space. And that's going to make it infeasible to solve our problem. So what's the scientific answer to this? The answer is that there isn't a scientific answer, and we'll have to go back to Tom Carden's finding the state is in the heart. Yeah, it's a balance. And I guess this is looking at your problem and seeing if you can get a model that works for your data or a given state, or whether you need to expand it or maybe contract it. And then if you do need to expand it, maybe you can expand it, but then maybe you can apply some better tricks afterwards to kind of reduce dimensionality like we did with the job search. We'll talk about that as well.
So, yeah, if the state includes other agent action.
I'm only going to talk about single agent problem. Yeah. That's going to take us just a little bit too far. It's a really good question. But let me just stay within the confines of my single agents. Any other questions or comments? Okay, so I'm sure you're getting a little bit tired and starting to think about lunch, but let's push on for another 10 minutes or so. And trying to work hard and absorb as much of the boring definitions as possible. And once we've done that, we'll be really well placed after lunch to dive into the algorithms, which is much more fun. So let's work a bit more. Okay, so let's define things a little bit formally. So a Markov decision process for us is going to be this feasible correspondence, the discount factor, the reward function, and the thing I call the stochastic term, which is just the thing that gives us a distribution of tomorrow's state, given the current state. So put these things together, we get a Markov decision process. Those are the primitives. And beta, I'm always going to assume that it's strictly less. All of the theory will depend on that. Okay, and then the Markov decision process is going to evolve like this. We start with an initial state, and then I say, well, here's left infinity, in other words, looping forever. I'm going to focus entirely on numerical horizons here. You can actually embed finite horizon problems in numerical horizon problems. Just by having an extra state variable. So there's not much loss of generality by focusing on infinite horizons with a theory system. So infinite horizons, going around forever, we observe the current state, we choose an action from our feasible set, we get a reward, the state updates from this distribution, which is affected by our state and action, and we go around again. And we try to maximize lifetime rewards. In this setting, Bellman's equation looks like this. That's our really standard Bellman's equation. And Bellman's principle of optimality tells us that if we take a value function and we put it in here, and we solve for the maximal actions, we're going to get an optimal place. And when we behave optimally, we're going to get maximal lifetime value starting from state X. So the brilliance of Bellman's principle of optimality, again, reduce an infinite horizon problem to a two-period problem. This is a two-period problem where V is your terminal results. It is. All the dynamic programming is reduced to finding the right terminal function for the two-period problem. All right, here's a little example about taking, and I'm actually going to skip over it. We'll do something very similar later. The point of these couple of slides is just to say every problem that, maybe it's not fully saying this, but like most of the problems that you deal with day to day, even though you look at the Bellman equation, it looks a little bit different to the one that I just showed you. There's a way of like transforming that into a Markov decision process. So I just have to say, oh, this is the reward function, this is the stochastic kernel, this guy's gamma, and we can make it work. So we don't need to go through the tedious details of that, but the point is that for standard kind of problems that we're going to be considering, as long as lifetime utility is aggregated in the way that I said, that's going to be a Markov decision process. And therefore, all of the theory that we talk about applies, and all of the algorithms that I'm going to discuss also apply. So let's look at that. The job search problem also be framed with a Markov decision process in the optimal topic problem. Okay, so our aim now is just to define optimality and state the basic optimality results. Maybe say what value function integration is in this context. And then we'll be good for the afternoon session. So stick with me. Okay, so policy, we know a policy is a map from today's state into an action. Map from states to actions. We're going to call it sigma. One thing to be really clear about from the start is that if I pick a sigma policy, I'm committed to it for life in this model. So policy, if I say this is a function, if I see this state if I see the state at any given time, I'm going to react like this. And later, if I come back to that same state, I'm going to react in the same way. Why would I do that? Because I'm looking for something horizon. So I'm going to choose a policy function which tells me how to act in any state of the world, and I'm going to stick by it forever. In reality, I choose policy functions like I'm going to go to the gym every morning at 6 a.m. and then I stick by it for like 2 days and then I can get it done. With this model, we apply it forever. And then a feasible policy is a policy that respects the feasibility constraint. Now, let's say we've picked the policy, calling it sigma. How does the state update? Well, now the actions are prescribed by the state. The state is going to update like this, from here and here to updating loop. And that's just the function of x. So if I define this p sub sigma to be the updating rule when I follow policy sigma, if you look at that guy, this is exactly a Markov matrix or a stochastic matrix. It's a matrix or a Markov chain. So when we pick a policy, we're actually choosing Markov chain. So the problem of dynamic programming is, or at least Markov decision processes, is to pick your favorite Markov chain. In terms of the one that gives you maximal life. Once I pick sigma, I know the dynamics. I know the dynamics have a state standard. Okay, so that P sigma now, that's the dynamics when we follow this policy. And our state, let's say our state's going down. And our rewards at X are also prescribed by sigma. Once I know X. Rewards are now just a function of X of the state, because I know I'm going to act at every state. So I'm just going to write R sub sigma here to remind me that this is now just a function of the state. Rewards are a function of the state, given the policy. And now I can compute this expected reward, T. And then I'm conditioning on starting at with X. So that's the starting condition. Well, when I first saw dynamic programming, because I was so confused, like A is a random variable, and then what is this expectation like? What distribution are we taking expectations? What are we integrating with respect to? But this is basically neat. If I take expectations here, well, this is just expectations that under this particular policy, R sub sigma of X. And I'm just taking expectations from Markov chain. I know how to do that. And just looking at the time t distribution. And to get the time t distribution, I just take powers of the matrix. So pt is p multiplied by itself t times. That gives me time t distributions. Okay. So I'm just integrating or summing with respect to that time t distribution. And in the last equality, I'm writing that using matrix notation. The resolution is not as good on this side of the screen. So yeah, this is just, I'm just writing it in a different way. Like these are matrix, but I know that I'm writing my matrices, like normally it's going to be an I and a J and then be subscripts. Right? But you can forgive me for deviating a little bit from that. The reason I'm deviating a bit from that is A, this notation turns out to be easier, and B, once you do shift to continuous state spaces, nothing changes except that you swap out sums for integrals. It's a bit easier to jump from one to the other if I just write brackets instead of subscript. So that's all it is. Right, so this is just, I just take R, the vector, I take the vector R. I take the vector R and I do that. This is just matrix multiplication. This is the vector. This is the matrix. That's what you get. This is row number X. Anyway, the details don't matter too much, but basically I can convert this expectation into something that I can compute easily. All right. Let's push just a tiny bit further. Let's push this one more step, this idea. What is the lifetime value of following given policy sigma? Well, the lifetime value of a given policy, and I'll denote that by B sub sigma of X, is just, I'm going to take the expectation of all of these gifts, summed and discounted. And this is the sum, I can put the expectation through the sum, and then we've already know what this is. We just did that. So now working out lifetime value of policy is easy. The lifetime value, here I'm dropping the X. The X here is just the row, the vectors. These sub sigma the vector. And I'm just dropping the X here and writing it. This guy is the matrix multiplied by the power of P, this is the column vector. And now, if you remember from basic Neumann series theory, this is just a geometric sum, right? Imagine, are you guys familiar with this? All of the eigenvalues of this guy is strictly less than 1, which is going to be treated as less than 1. Then this guy is equal to this guy. If you're not familiar with this, then imagine that this is just a number. And imagine that that number is less than 1. And this is a geometric series, right? Then this geometric series would be 1 over 1 minus the number. Yeah. So this is just the matrix version of basic geometry. Okay, so then I know exactly how to compute lifetime value now. And now I know how to compute lifetime value. I know how to maximize it. Oh, no, I guess I got wrong. I can at least think about maximizing this now. If any sigma in policy I choose, I can compute value. And now I can start looking around at different policies saying, I wonder which one gives me the best value. Now, I believe that in some of the artificial intelligence literature now, they're just doing straight searches in policy space. They just take policy space and then they approximate things with a neural network. And they just do hill climbing in policy space, searching for the optimal policy. And I'm kind of curious because the way that I'm going to think about this problem is more systematically using the theory of leadership and dynamic programming. So I find it kind of interesting that they're going to put aside all of the theories that I've talked about in the algorithms and just do hill climbing in the space of policies, trying to maximize this thing. And I kind of, if I think about that, I wonder why they're doing that. I suppose one thing is that we care fairly about trying to find something that's close to the maximum. Otherwise, we feel a little bit insecure about what we're doing. Whereas they try and beat the best chess player in the world. Using the analogy of John Ross and it's all of that stuff, like the AlphaGo and so on, that's solved using these techniques. Actually, they don't do straight hill climbing, they use another algorithm. But there in that world, if you beat the best chess player in the world, you don't care if the optimum is somewhere up here. You're already doing better than everyone. But we didn't care a bit more about trying to get so we'll come back to that and we'll define optimality and then we'll look at a few different algorithms. And then we'll look at dimensionality reduction and then we'll look at implementing this stuff on a machine using Python in the afternoon session. Okay.